La segunda presentación, invitamos al Centro Internacional de Conocimiento sobre CCS, que está basado en la provincia de Saskatchewan a partir del proyecto de Boundary Dam, que es una central a carbón. Debería estar en línea CONWAY HandsOn, que supervisa un equipo de ingenieros y especialistas en el centro de proyectos dedicados a hacer avanzar la tecnología de captura de carbono en diversas aplicaciones industriales. Antes de ingresar al Centro del Conocimiento, Conway trabajó durante más de 2 décadas en Sask Power, que es la principal empresa de servicios eléctricos en la provincia de Saskatchewan. Durante ese tiempo dirigió y gestionó con éxito grandes equipos de ingenieros y especialistas en gestión y control, supervisando proyectos de capital relacionados con la generación de energía, incluidas nuevas construcciones y CCUS. Conway es licenciado en Ingeniería Mecánica por la Universidad de Saskatchewan y tiene un título profesional de gestión de proyectos del Instituto de Gestión de Proyectos. Conway, si estás en línea. Yes. Hello, Conway. The floor is yours. Welcome.
Great. Thank you. Thank you very much. Muchas gracias. And that's the extent of my Spanish. But I'm happy to be here today and to talk to you a little bit about carbon capture. My organization focuses more on the carbon capture side of things, and that's really what I'll get into. It's kind of building on some of the things you've heard about storage and the economics that GLJ just went through. So a little bit about the Carbon Capture and Storage Knowledge Center. We're a small nonprofit organization that were started shortly after the Boundary Dam Unit 3 CCS project started in Canada, in Saskatchewan. So that was one of the world's first carbon capture projects. It's been operating for almost 9 years now. And our company was essentially started to share with others what SaskPower learned going through the development of that world's first project. So we just provide advice to people throughout all stages of a project, from feasibility, pre-feasibility, feed studies, and then as people get into construction, there are a number of things we learn on that project that will be of benefit to people as they move through those stages. So this is a picture of the Boundary Dam Unit 3 facility itself. You can see this is a large power plant here in the middle of everything. So there are six units in this facility originally. There's Unit 6 here, Unit 5, Unit 4, and Unit 3. Unit 3 has the CCS facility added to it. And you can see this is the CCS facility over here. So this is the absorber towers for the liquid amine post-combustion process. This is the capture and compression building. And there's a heat rejection building back over here. So this picture gives you a bit of an idea of the scale of these projects. They do take up a lot of surface. There's a lot of infrastructure required to capture CO2. This facility was designed to capture about 1 million tons per year of CO2. It was designed for a 90% capture rate at the time. And so far it's stored over 5.5 million tons of CO2. Another little bit of a picture and a little bit more background on the Boundary Dam Unit 3 project. So it life extended an existing 45-year-old coal-fired power plant. So it's coming to its end of life. SaskPower had to make a decision about where to source new electricity generation, and they actually compared putting carbon capture on Boundary Dam Unit 3 with building a new natural gas combined cycle plant. And at the time, natural gas was quite expensive in Canada, and it actually made financial sense for SaskPower to go ahead with the BD3 project. And I'll talk a little bit about how and why. But the total capital investment for the project is $1.5 billion Canadian, and it was aided by about a $250 million grant from the federal government. The project itself was executed in 2 parts. There was about $600 million went into the power plant over here, and about $900 million went into the capture plant and building all that new equipment and infrastructure. And again, operations started in October 2014, so that facility has almost been years now. And we've certainly learned a lot through the development of the project, the construction of the power plant, and then ongoing optimization support that we provided for SaskPower over the last 8.5 years of operation. So the CO2 that's produced at Boundary Dam Unit 3 is used for both enhanced oil recovery, and it's also stored in a saline aquifer for long-term, just to essentially to prove long-term storage. And SaskPower wanted a second avenue for their CO2 as opposed to the EOR. There were some limits in the original contract in terms of how much CO2 would go to enhanced oil recovery. So this Aquastor well has been studied by people from all around the world, and it's a really good source of information in terms of proving the safe long-term storage of CO2. They've seen no seismicity, no real issues with that long-term storage. And similarly, the enhanced oil recovery facility in Weyburn-Midale, they've been storing CO2 there since the early 2000s. And they've stored over 38 million tons of CO2. And again, it's a really good source of information in terms of showing the safety and security of long-term storage of CO2. This is a pretty busy diagram that goes through sort of the high-level process of the Boundary Dam Unit 3 project. And I'm not going to walk through every item here. You'll have a copy of the photograph for future reference. I'll just point out a few highlights. So any CCS project, and we're talking about post-combustion CCS project, starts with combustion of some sort and producing some kind of a flue gas. The flue gas typically gets pre-treated in some way, and in SaskPower's case, the pre-treatment consists of this dust collection unit here, which is a dry electrostatic precipitator. It also consists of this SO2 absorption unit, which is actually another amine loop to capture SO2 prior to an amine system that captures the CO2. So these are the two key pre-treatment pieces of equipment that SaskPower utilizes, is this SO2 system, which actually produces sulfuric acid that SaskPower can sell as a byproduct to help with offset the cost of operation, and then this dust collector. And every facility, and I'll talk about this quite a bit, every facility needs a different level of flue gas pre-treatment to make sure that the CO2 capture system works effectively. And we've learned a lot about that in 8.5 years of operation. The heart of this liquid amine post-combustion process is the CO2 absorber and the CO2 regenerator or stripper. So the amine interacts with flue gas in this vessel. The amine absorbs CO2 out of the flue gas, and then the flue gas comes out the top of this stack with essentially, in this case, 90% of the CO2 removed. At times, it's actually above 90% at Boundary Dam. And the new number that the industry is really working with is a 95% capture rate. So it has stepped forward since this project was built 8 or 9 years ago. The CO2 stripper, the amine gets reheated. The reheating of the amine causes the CO2 to get released. The CO2 comes off the top of this stripper vessel. It has to get dehydrated. It's quite moist, so all the water has to be taken out. And then there's a major compressor. This is the other big piece of equipment. This compressor is, in SaskPower's case, a 15 megawatt engine driving this compressor. And it compresses the CO2 to a dense phase or a supercritical state. And that pressure is about 2,500 psi or about 170 bars. So it's a very high pressure CO2, essentially behaves like a liquid. There are a lot of complexities around compression and transportation of CO2. There's about a 70-kilometer pipeline that takes the CO2 over to the Weyburn-Midale facility where it's injected about 1.5 kilometers below the surface for enhanced oil recovery. And then the Aquastor well is quite a bit closer to the power plant. It's about a 3-kilometer pipeline, and it goes much deeper, 3.4 kilometers deep. And again, these are great sources of information in terms of the safety of long-term storage of CO2. The other piece of equipment is cooling. These amine systems are very energy intensive, so there's a lot of cooling and heating energy that's required. So the cooling tower is quite a big piece of equipment, and then the heat required over here to reheat the amine is another big piece of energy that's required for the system. And another thing I'll talk about is thermal integration, and if there are any opportunities with the existing process to utilize heat that's maybe being discharged to the atmosphere, that's something that we definitely recommend people look at. In SaskPower's case, their flue gas comes out of their boiler quite hot. It's 350 or so degrees Fahrenheit, and that's way too hot for the amine process. So it needs to have a lot of energy extracted out of it before it goes into the amine process. They were able to take that energy, bring it back into the power plant, and use it to preheat some of the water that goes into the steam cycle to produce electricity. And they gained about 4 megawatts of electrical generation on a 150 megawatt unit by doing that thermal integration, that heat integration. So it's very important to consider any opportunity for heat integration so that you can minimize your operating cost in the longer term. Some of the successes and challenges for the Boundary Dam Unit 3 project. So this, again, it was a world's first project, and the technology had been used largely in the oil and gas sector, mostly for gas sweetening for decades, and in Canada certainly, and likely in Argentina as well. It's been used for a long time, and people really understood it very well in that application. Applying it to flue gas is a much different application and required a different level of understanding. This process was scaled up for Boundary Dam Unit 3 7,000 to 1. So it was a major step forward and a little bit of a leap of faith. That a lot of risk mitigation work was done during project development to make sure that the process worked, and it did. It did work. I talked quite a bit already about thermal integration, and I talked about the flue gas cooler. The flue gas cooler was seen as one of the highest risk pieces of equipment, and you can see some of these tubes are from a flue gas cooler that was installed in Thailand, and they failed very prematurely. There's some acid gases in coal-fired power plant flue gases. Once you cool the flue gas to a certain level, those acid gases start to condense, they form acid, and the acid essentially destroyed these flue gas coolers. So the design of Boundary Dam 3 was actually a cooler with Teflon tubes, and in the 9 years almost of operation, there haven't been any issues with that cooler. So that was a pretty significant success for SaskPower. Regulatory permitting. So when this project was built 8 or 9 years ago, and it's actually not much different today, there isn't a hard and fast set of regulations for permitting the operation of a carbon capture facility. So understanding what's allowed in terms of air emissions and water emissions. A lot of work was done by SaskPower to work with their regulator and essentially educate them and mutually come up with a regulatory policy that would allow this unit to be permitted. Transition to operations. This was a key challenge for SaskPower. I think it's less of a challenge in the oil and gas sector, again, with the maturity of the process engineering knowledge in the oil and gas sector. I think it's a shorter leap to make. In the power sector, SaskPower had people that were really good at turning coal into electricity, and they were rather afraid of this complicated chemical process. So it took a lot of training. They started early and had a dedicated team of operators trained on chemistry, and they spent a lot of time getting ready for operations, and that went quite smoothly. On the challenges side of the equation, if we were to distill down the challenges for SaskPower into one word, that word would be fly ash. And fly ash is the ash that's produced from combusting coal. There, as you will remember, there was a dust collection unit downstream of the power plant, a dry electrostatic precipitator. It removes 99.5% of the fly ash that's in the flue gas, but that remaining 0.5% still gets through the electrostatic precipitator. It ends up in this closed loop amine process, and it causes problems. You can see from the photographs here, it causes some fouling of some of the equipment. This is a section of demister plate that's quite fouled. And then some of the packing in the absorber tower as well. It gets fouled up over time. You can do things to try to filter the fly ash out of the amine, but we found it's not possible to fully remove the fly ash from the amine. In addition to the fouling, the fly ash actually causes some problems with amine degradation that wasn't expected. And that is something that, again, if SaskPower could go back in time, they felt that they really understood their flue gas. As the other challenge here was flue gas characterization, and they thought they understood their flue gas very well, particularly the fly ash component of it, because SaskPower has sold their fly ash for years to the cement sector. So they really understood the chemical composition of the fly ash. What was missed in this application was the 0.5% of fly ash that gets through the electrostatic precipitator. It actually has a slightly different chemical composition, and it caused some unexpected reactions with the amine that accelerated amine degradation. So not only did it foul the equipment, it actually accelerated some amine degradation reactions. So that's been a big challenge for SaskPower. The other thing that was an issue for SaskPower was reduced capacity, which again comes back to the fouling issues of some of the equipment. There were also some economic factors early on where it wasn't economically desirable for SaskPower to maximize CO2 capture. That's changed. As you would have heard in the previous presentation, there's a carbon tax in Canada that's going up $15 a ton every year. It's $65 a ton right now. And avoiding paying that carbon tax makes it more attractive to maximize the CO2 capture. So hands-on technical expertise, this is some of the information that my team shares with people around the world that are developing these projects. And really our focus in sharing these lessons learned is to help people reduce their risk, lower their cost, and ultimately improve the performance of their project once it's up and running and in service. So we've worked with people across all different sectors, including the oil and gas sector. And I'll talk a little bit about some of the specific things we've done in the oil and gas sector. Some of the key things that we talk about with people or help them with is technology suitability and maturity is an important one. I'm talking a lot today about liquid amine post-combustion. That's the technology that was chosen for Boundary Dam Unit 3. And we would say today that's really the commercially available and deployable technology if you want to do a project in the very short term. There are other technologies being developed. There are dry sorbents being developed. There are membrane technologies, cryogenic technologies, a number of different things that are a little bit further behind and still in sort of the R&D stage, but they're advancing quickly. So we keep an eye on those things, and we help to advise clients in terms of their timeline. When do you need to do a CCS project? Can you afford to wait to see if something else comes up that's maybe less costly in your application, maybe less energy intensive? We help people with those conversations and those decisions. Flue gas characterization, it's repeated quite a bit in this presentation, and if you take one thing away from thinking about a carbon capture project, flue gas characterization is a key one. Just really understanding what's in your flue gas. Everybody measures their flue gas today essentially to satisfy their regulators. So you know how much particulate matter you're emitting, how much typically SOx or sulfur oxides you're emitting, how much NOx, nitrogen oxides, how much you're emitting of those. But you're only measuring it to satisfy the regulator. You're not measuring it because it's key to your process. When you add a carbon capture system downstream of your facility, suddenly that flue gas that was a waste stream you measured just to satisfy the regulator, that's a key input now into a detailed chemical process. So it's very important. I can't overstate how important it is to understand what's in your flue gas. The question of storage versus utilization, as you've heard a little bit about storage already, and we've proven long-term storage up here in Saskatchewan as well. There are a lot of utilization technologies being researched, from things like nanotubes or algae or different products that can be produced with CO2, and more work is advancing on that front. I think with the hundreds of millions of tons per year of CO2 that we need around the world to achieve our goals, there's always going to be a need for long-term storage. It would be great if we could have a combination of storage and utilization, and we can find a use for these tons and tons of CO2. And I think that day will come, but in the short term, we really do need to focus on storage, as you would have heard from the previous presentation. Thermal integration, I talked a little bit about that already. I won't talk about it very much more, but again, it's another key thing to think about as you're going into a project. Is there an opportunity to minimize my energy requirements by maybe using some energy that we're emitting to the environment without utilizing it? There's typically some opportunity there in a retrofit application. If it's a new build with CCS, then it's even easier right from the start. You can think about that integration piece. Variation understanding, this gets into the startup, the understanding and the comfort level with these sorts of processes. Again, SaskPower was not very comfortable. They put a lot of effort into transitioning to operations because it was something very new and very foreign to them. What we find with our oil and gas sector clients is they're much more comfortable with the process. They understand it to a much higher level, and they can make that leap a little bit easier. It's still different. There are a lot of nuances to treating flue gas with an amine system, but their process engineers are much more comfortable with the technology. So it varies across industries. I won't go through this slide very much. This is just the life cycle of a CCS project. We say typically best case, if you start a project, you have about a year of feasibility work, about 2 years of feed work, and then about 3 years of construction, commissioning, performance testing, executing the project, essentially. So 6 years total. I think that's actually quite an aggressive schedule. I think that's a challenging schedule to meet. That's assuming there are no regulatory hurdles, no major delays, no supply chain issues, which we're seeing post-COVID. So I think this is a very optimistic schedule. And this text down here, I won't go through it. This is essentially some of the things we do to help people through these various phases of a project. And as you can appreciate, 99% of the projects are over here in this purple area. They haven't moved forward into the the red area or certainly the orange area of operations. So some of the things we've done to help people in the oil and gas sector, technical workshops. So I always tell people this when we do technical workshops. This is my favorite thing to do at the Knowledge Center. We bring a group of interested people up. Typically they'll come and they'll tour the Boundary Dam Unit 3 facility with us. And then we'll spend about a day and a half walking through a 450 slide deck we've produced that documents a lot of the lessons learned from Boundary Dam Unit 3. They're exhausting. They're an exhausting 2 days. Typically people are quite tired afterwards, but there's a lot of really good conversation. A lot of things are learned and conveyed both ways. Those 1 or 2 day workshops are a lot of fun. They're quite rewarding for my team for sure. I'm going to say it again, flue gas characterization. This is something we've done. We work with people to analyze their continuous emissions monitor, analyze what sort of data that they have already in terms of what's in their flue gas. Often that leads to a recommendation about testing their flue gas to a deeper level and measuring some of those constituents to down into the part per million range at some points, just to understand how much of these constituents are in the flue gas, because they can really impact the performance of the carbon capture system. Pilot testing, some people elect to do a pilot test, so they bring a small skid in, actually test the specific amine with their actual flue gas, and we provided some support to review the skid design, review the pilot test plan, those sorts of things, which are important to make sure you do it right. So the results that you get from your pilot test are actually applicable to your long-term application, and you've done things like test long enough. Many people test for a short period of time, and not always long enough for the amine degradation reactions to start to show up. Some of these things take a lot of time to happen. Technology selections, we've done this as well, helping people select, in this case, the right kind of liquid amine post-combustion technology for their flue gas, as well as screening technologies themselves. So again, I mentioned some of the developing technologies, the dry sorbents, the cryogenic processes, the membrane processes, understanding what type of technology is right for a client. We've done that work for folks as well. So I've talked a lot about my team at the Knowledge Center. We're a technical, an engineering team helping people with the nuts and bolts of how these carbon capture projects work. We also have another part of our organization that provides strategic advice. So they'll go through and help people interpret the regulatory requirements of their country, understanding if there are funding opportunities, what sort of government support, and the GLJ team, we're talking a little bit about some of the funding opportunities available in Canada. And lastly, the public and stakeholder engagement piece. Carbon capture is a relatively new technology that people are developing around the world. And anytime something new comes, it's sort of inherent on the industry to educate the public and let them understand what the risks are, what the real risks are. We're seeing a lot of pushback around CO2 pipelines, CO2 storage right now, particularly the United States is quite active in this area. We think the carbon capture sector as a whole needs to probably do a better job of getting in front of this and educating the public about where it's been done safely, how it's been done safely, and try to prove that it's not something to be overly concerned about, and there are ways to make sure that it's safe. That's a piece that I think hasn't probably advanced enough yet. So just building a little bit on the collaboration required to advance a CCS project. Devin talked quite a bit about the economics of a CO2 project in Canada, and every jurisdiction is different in terms of what's available for. We use the terms carrots and sticks. So the regulatory requirements and rules and things like carbon taxes are sticks. Things like in Canada, the investment tax credit, or in the United States, the 45Q, are some of the carrots that help companies offset the cost of these projects and build a business case. Particularly for the oil and gas sector being a globally traded commodity, it's very challenging when some jurisdictions have a lot of support for CCS projects, other ones don't have support for CCS projects. It's hard to make to be competitive in that global market. And other countries don't even require things like net zero requirements or aren't as far advanced. So it's a really challenging. It's a challenging time for the oil and gas sector, and specifically because of that, because of the differences kind of globally. But one of the things that we do help people with is understanding those carrots and sticks in their jurisdiction, what does it take to get a project across the line in terms of final investment decision? What do you need to do to satisfy your shareholders or your board of directors, your investors? And what opportunities are out there to fund these projects? Lastly, I talked a little bit already about stakeholder engagement and building public confidence. I don't know that people are very aware of carbon capture and how much it's been done around the world already, how much CO2 has already been sequestered in the world. And again, in jurisdictions where the geology is favorable, like a good portion, large portions of Canada, large portions of the United States and Argentina, where you know that you can safely store the CO2. It's a matter of getting that message in front of the public and understanding that, you know, our geoscientists have done this for a long time. We understand the security of the subsurface. The cap rock is tight enough, and we know that CO2 is going to stay down there. And by the way, here's some examples where people have been doing it for decades, and it's been proven to be safe. I think getting that message in front of people is very important. I will end there. I really appreciate the invitation to come and speak to you today about carbon capture. Muchas gracias, and that's the end of my Spanish again.